I hate to break it to you guys, but up to this point, I've been lying to you, at least partially, but not intentionally and not meaningfully. When we start teaching chemical reactions, we use a single arrow, meaning every single molecule of nitrogen that could possibly react with this hydrogen produces that ammonia. The reaction goes to completion. Everything that could possibly react does react. However, in reality, most reactions don't go to completion. They actually establish a state called equilibrium. And it's not a state like a state in the country, it's a state like a state of being. And it's based on the rate of the forward reaction versus the reverse reaction. Now you know that some reactions are faster or slower than others. So most reactions that you think as going to completion actually just have a very swift forward reaction and a very slow or unlikely reverse reaction. Now equilibrium is actually nothing new to you. You have seen it before, at least if you've ever been to a gym. A treadmill is a state of equilibrium. When you are on a treadmill, you exist at a state of equilibrium, because the rate at which you go forward has to equal the rate at which you go back. You've established a balance between those two rates. And as long as you stay at that set speed, going forward at the same rate at which the treadmill is going back, you stay on the treadmill. And your equilibrium position, where you lie, where you are, does not change. And from a chemical standpoint, you can stay at equilibrium indefinitely, as long as nothing around you changes. And this is because systems at equilibrium will stay at equilibrium unless there's a stress put on them. Also, systems at equilibrium are said to be dynamic. They're constantly moving. The forward reaction is always happening, and so is the reverse reaction. Just as you on the treadmill, no matter how exhausted you get, in order to stay on that treadmill, you must keep moving forward. If you were to stop, then you're going to have your feet flown out from underneath, which will usually happen to some disastrous effect. Equilibrium is a measure of rates. It has nothing to do with concentration or with the mass of something. Just because your reactant's mass equals your products does not mean you are at equilibrium. It has to do with the rate of the forward reaction versus the rate of the reverse reaction. Harry LeChatlier, or LeChatlier, and Carl Bloom are two scientists that studied equilibrium and systems at equilibrium independently, and both came up with the same repeated observations, that a system at equilibrium will stay at equilibrium and will adjust where it lies if a stress is placed on it. So let's go back to our treadmill example. If you're on a treadmill and I come along and I increase the speed of the treadmill, you are going to have to speed up in order to keep up with the treadmill. You will work to undo the stress I have applied. This is LeChatlier's principle. So what are some stresses you can add to a system at equilibrium? Well, let's look at our good friend, my favorite chemical equation, the Haber process. And yes, I had to switch some things there. Now, any stress, a stress is anything that is going to speed up either the reverse or the forward reaction. So let's go with the forward reaction. If I add more reactants, that's placing a stress on my reactants side. I'm adding more reactants. Those collisions between the hydrogen and the nitrogen are more likely to happen now. And because of that, the system's equilibrium shifts towards the products to produce more products. And it's going to use up some of that hydrogen to do that. So my concentration of products increases, my concentration of hydrogen is going to decrease because I'm going to be using that hydrogen up. What if I removed some nitrogen? Well, I remove some nitrogen, so that frees up some space. More of this ammonia can break down. So if I remove nitrogen, the system is going to shift its equilibrium to favor the production of reactants, to use up that extra room you just opened up. So my concentration of ammonia is going to decrease. My concentration of hydrogen, because I'm producing more hydrogen, is going to go up, and it's going to try to undo that removal of nitrogen, trying to reestablish that equilibrium. If I remove some ammonia, now that frees up space, or the system needs to remake that ammonia. It's more likely that these nitrogens and hydrogens will collide, so the system's going to favor the production of ammonia, and it's going to shift towards products. So my concentration of nitrogen and hydrogen will go down, while my concentration of ammonia after the removal is going to increase. So changing the concentrations of either your reactants or products can shift equilibrium because it is a stress. So think of it as the collision theory, or at least from that angle. Temperature can also play a part in equilibrium, or actually plays a very large part, because a system establishes equilibrium at a set temperature, and if you change that temperature, the system is going to shift its equilibrium depending on whether it's exothermic or endothermic. So this reaction here is exothermic because I have a unit for delta H that's on my product side. And not only that, it would be a positive delta H, or sorry, it'd be a negative delta H because it's a product. Whew, I'm a little tongue twisted. If I cool the system down, you can treat that as either a reactant or product. Treat the temperature as a reactant or product. In this case, I have this delta H value as a product, so cooling it down, we're just going to treat the same as the ammonia. If I cool it down, it's like removing some temperature. So my temperature goes down. The system is going to try to undo that stress by favoring the production of products. So my concentration of nitrogen and hydrogen are going to decrease, and the system is going to try to warm itself back up by increasing the amount of ammonia produced. If I heat the system up, that's like increasing this delta H. And since it's increasing that delta H, the system's going to work to undo that stress and use that heat to produce more product or more reactants. So my concentration of nitrogen and hydrogen is going to increase while my concentration of ammonia is going to decrease. So the system is going to work to cool itself down by using that energy, that heat. If I increase the pressure on the system, it will only play a part for the gases involved. So if you have a system of all liquids or all solids or all aqueous, increasing pressure is going to have no effect whatsoever, or very little effect. But if you have a system that involves gases, increasing pressure is going to shift the equilibrium one way or another. Increasing pressure on a gas decreases its volume. So when you increase the pressure, the volume of the container decreases. And so the system is going to favor whichever side of the reaction contains the least moles of gas. So I decrease the volume, and so this increasing pressure decreases the volume. I'm going to favor whichever side of the reaction contains the least moles of gas, in which case is the products. So equilibrium is going to shift towards the products, and my concentration of ammonia goes up while my concentration of nitrogen and hydrogen go down. If I decrease the pressure, that opens up more space for the reaction to take place. That means the equilibrium is going to shift to favor whichever side of the reaction contains the most moles of gas. So for this reaction, it will favor the production of reactants, and my concentration of ammonia will go down, my concentration of hydrogen and nitrogen will go up. What if I add a catalyst? What's going to happen to this system then? Well, a catalyst lowers the activation energy of the forward reaction, but it also lowers the activation energy of the reverse reaction. So the forward reaction will happen faster, the reverse reaction will happen faster, but overall there's going to be no change in the equilibrium. So adding a catalyst does not shift the equilibrium. What if I add a small amount of an inert gas? What will happen to equilibrium then? Well, inert means non-reactive. So this gas is not going to react with either my reactants or my products. So once again, there's going to be no change in the equilibrium. So just to review, reactions can happen fast or they can happen slow, but when the forward and reverse reaction are happening at the same time and reach a state at which they are stable and not changing, this is called equilibrium. It is dynamic, meaning it is in constant motion, constantly going forward. The forward reaction is constantly happening. At the same time, the reverse reaction is constantly happening. And a closed system will stay at equilibrium indefinitely unless a stress is put upon it. And depending on what that stress is, it could shift to favor products, such as when you add more reactants or remove some product, or shift to favor reactants, such as when you add more products and remove some reactants.